Alright, so here you have the window of the educational version that you see when you open it up. And so first thing, just to give you a little orientation, normal Windows kind of scenario, you've got a bunch of menus at the top, and then you've got a couple rows of graphical icons. In the top left here you have your coordinate system, your global coordinate system X and Y, and then what you see here in gray is the grid. This is a drawing grid. So the first thing that you're going to want to do, if you take a look at your or at my description here of what we're supposed to do, is the first thing is we're going to create the geometry. So if we take a look at our system, you can do this two ways. You can actually draw it on there, or you can create the joint coordinates by typing them in. So first thing I'm gonna, and then the other thing I should mention is there's this little floating menu box. If you have multiple screens, you have to be a little bit careful that the floating menu box shows up on the right screen, and it just gives you sort of some shortcuts to different things. So the first one I'm going to click on here is joint coordinates, and it gives me this, and it says no data. So, but if I click anywhere in here, it gives me a label. My first one, I'm going to change the label to A, and A is going to be at 0, 0. I'm going to hit enter. B, we know from our drawing, is 12 feet up, but still X is 0, so that's 0, 12. Hit enter again. And the next one is C, 10 feet up. C is 12 feet over, 10 feet up. And D is 12 feet over and 2 feet up, right? It's 10 feet up and 8 feet down, so that's 2 feet up. And so we see those pop up on our grid here. Now, up here there is a little, one of the icons. If you just sort of hover across the icons, we have some zoom control tools. We have this little pencil here, which is to turn on or off the graphics editing toolbar, which is the one down below here. We have a redraw full model view. That's kind of nice because it zooms into the model. We can save view or recall view states, so that's like with something's on and something's off. We can turn on and off the loads. There's a bunch of stuff I'll talk about later. Turn on and off the boundary conditions, turn on and off the members. The one we're after at the moment is the joint labels, which is this one with an N. And so if we do that, and then we take a look down here, it gives me the A, B, C, and D show up. Right? So the next thing we're going to do is I'm not going to use the grid in this case. The grid is only useful when you're drawing members. And so, well, actually, before I do that, I'm going to go ahead and draw some members, right? So down here on the graphics editing toolbar here, we have a couple things related to the grid. You can modify the grid. You can turn the grid on and off. Then we have draw new member, modify member, modify boundary. This is draw or modify boundary conditions, and then apply three different types of loads. And then there's also delete some members. So if I go ahead here and click on the draw new member, now in the full version of RISA, this is not exactly what happens. It's a little different. But in this case, what it does is it asks me for the area, the moment of inertia, and the modulus of elasticity, or the Young's modulus of the material. So if I go back to my my thing here, so this my example problem is I'm using 6x6, 6x12, and 4x4 timber beams, and so I've given the modulus here and the sizes. If you're aware of timber beams, they're actually not, these are the nominal sizes, the actual sizes are given here. And you'll recall, of course, that the area is just the base times height. So for a 4x4, it's just 3.5 times 3.5, which comes out to be 12.25 inches squared, which I've given up on the top right. The moment of inertia, you'll recall from mechanics, is 1/12 base times height cubed. And so for the 4x4, that's just 1/12 times 3.5 inches times 3.5 inches cubed. And that comes out to be 12.5 inches to the fourth. Right? So I've listed those all up in the right-hand corner there. And so I'm going to draw AB first, and so I'm going to put in my area. And so my area there is going to be 12.25 with a moment of inertia of 12.5. So 12.25, 12.5. And then my modulus, I said, was 1500 KSI. And I'm going to leave these as fixed, because that's how they are connected to each other. I didn't put it, I'm not showing any hinges in the model. So I've drawn the first member. If I draw the second member is a 6x12, so it has a area of 63.25 and a moment of inertia of 697. And so 63.25 and 697. And so then I'm going to draw that member from B to C. I click on B, I click on C. There we go. And then finally, I'm going to, my final member is a 4x4. Oops, I did that wrong. So my first one was supposed to be the 6x6, which has an area of 30.25 and a modulus of 76. And my last one is actually supposed to be the 4x4, so let's do that one again. So my 4x4 was 12.25. And my moment of inertia was 12.5. And so then I can draw that guy from there to there. The other thing you'll notice here is once I have a member, I can, this little pencil here, I could draw other members using the grid, right? So I could have, started with the grid if I knew my dimensions. If I knew my member properties, I could start by entering a member and then drawing the whole thing. In this particular example problem, it's kind of a pain because every member is different, right? So it's the easiest when you can just draw a whole, you define a single member size and then draw a whole bunch, right? So I want to get rid of these now. I click on the delete parts button. You can delete based on different things. You can delete joints, delete loads, you can delete etc., members. I want to delete by clicking, so I just click this radio button down here, I say apply, and then I'm going to click on all the joints and members that I created that I don't want. In fact, now that I'm done with that, I'm actually going to get rid of my grid. So up here in the top left, there's a toggle grid. I'm going to turn my grid off, and then I'm going to zoom in with this little thing with the 4 arrows button, and so now I have a bigger version of my drawing, right, or my model. So, okay, so now my member here, my left-hand member AB is still wrong, and so there's a couple of ways to fix that. The easiest one is this little guy here with a question mark that says modify members, and so I'm going to change that to 30.25, and I'm going to say yes, I want to use that, and I'm going to change the I to 76.2. Yes, I want to use that, and then I can apply them by clicking individually, so I'm going to apply it to that one. Now, the unfortunate thing is that it's hard to tell if that worked, right? One way to tell is you can click on the members button here, and it tells you all the information about that member, right? It tells me the area that I have, the moment of inertia that I have, the Young's modulus that I have, and what joint it goes from. So I could go in here and I could actually edit it here as well. And this goes back to my discussion that you can modify things graphically or in the spreadsheets or numerically, and they are complementary. So, okay, so I have a structure, and the next thing I want to do, if I take a look at my my list here, is that I want to input my boundary conditions, right? So this little green guy in the graphical toolbar here is boundary conditions. So if I click on that, I end up with this. It says what's your X, what's your Y, and what's your rotation. Well, my model tells me that I have a fixed rotation, a fixed condition on the left, so I'm going to click this little fixed, and it automatically updates all three of those to fixed. And then I'm going to click apply, and then I'm going to draw a little box around A, and I get a little symbol there that says it's fixed. I'm going to click on the modified boundary conditions again. This time I'm going to click on pinned, and you'll notice that the rotation changes to free. So that's the definition of a pin, right? X and Y are fixed, rotation is free. I'm going to click apply, and then I'm going to box around D, and it gives me a little pin symbol. So I'm now done with my boundary conditions. And so the next thing I'm going to do is I'm actually going to make this window a little bit smaller so it centers it properly. The next thing I'm going to do is apply my loads, right? So I've got 3 load buttons. I'm going to start with the distributed load, so that's the middle one. My distributed load is in the Y direction. In this case, it's the global Y, which is the big Y. The magnitude is negative 0.6 kips per foot, right? You see in my model that it's 600 pounds per foot. That's negative. That's 6.6 kips per foot, and it's negative because it's down, right? Positive, as shown here, is up, so I want it to go down. I'm going to leave my start and end location 0. That's going to give me a distributed load on the entire length of the member. If I wanted it to end halfway through, I could put in that I could put it in 6 feet at end, and it would only put the load on half the member. So I'm going to click apply, and then I'm going to click on BC, and my load pops up. The second one is the joint member, so I'm going to click on the little red arrow here, and I want that to be in the X direction, and I want that one to be 3.1 kips, but it's actually negative 3.1. Again, it's to the left, positive X is to the right, and so I'm going to click on, now I'm going to box around joint C, and there it goes. I get my load of negative 3.1 kips. And then finally, the point load on the right here is a member load, and so that's a load. So I can't apply a joint load to come up with my final load there because it's in the middle of a member and I don't have a joint there. So I'm going to click on the member one. You'll notice that the direction here is little y. So in this particular case, I actually want it in the big X direction. So little y is the local coordinate system. And so in this case, because the member is vertical, that would actually be, well, it could be to the left or the right, depending on how I drew the member, right? So in this case, big X and does not align with little x, right? Little x is up and down, it's the length, it's the local coordinate of the member. Big X is left and right, right? So I want a big X, and I want it to be negative, and I want it to be 0.8, which is 0.8 kips is 800 pounds. And the location, I want it to be at 4 feet. And then I'm going to apply that, and then I click on my member, and it pops up. Again, you notice that they're 2 different colors because one is a member point load and the other one is a joint load. Alright, so now if I take a look again at my analysis, it says that I need to apply load combinations. So in this particular version of RISA, you don't have to apply load combinations. So when I do this example in the 3D version of RISA, I'll show you how to do that. But in this case, and in general, in the beginning of this course, we don't do any load combinations. That's more of a professional thing. Analysis options, again, there's not really any analysis options in this particular version of RISA, so we can just move on to solving it. And you'll notice here up at the top that there's a green equal sign. That's my solve. So I click on that, and it's solved, and I can only really tell that it's solved because there's a new box here of results, and then there's also a couple of blue boxes here on the top left that talk about details. So reviewing my analysis results, so this is a nice place where I can explore some of these buttons up here. So a couple of things I'll just kind of go across. So we can turn on and off the the joint labels. We can turn on and off the member labels, right? We might want to know which one is member 1, which one is member 2, etc. We might want to know which end is which. So that's a little bit more of an advanced discussion, but each member has an I and a J end, or if you prefer, a near and a far, and so the red and the blue kind of indicate that. You can also tell the A, I, and E. You can't do that on the full version, but here you can. It shows you what you got. You can turn on and off the boundary conditions. Not a huge amount of reason why to turn that off. You can turn on and off the coordinate system. Again, not a big reason. And then there's a little space and it gets into the results ones. These are grayed out until now because I have a solution. So the first one is the deflected shape. So if I click on that, I can see in magenta, I can see my deflected shape. And here is sort of the power, right? So you can see this is a nice deflected shape here. And you can see it very easily. And so you can turn that off then. The next one is axial, right? So you can see very easily here the axial force diagram, right? So we've got 5.1 kips of compression in this member. Actually, in fact, it's all compression, right? All 3 members are in compression. I can turn that off, and then I can turn on my shear diagram, right? And that's kind of what we would expect. We have constant shear in the legs, a very sloped shear, or a constantly linearly varying shear in the member with the distributed force. And then finally, we can see the moment diagram, right? And one of the things that I'll talk a little bit more about later is that RISA moment diagrams are actually inverted from normal moment diagrams or conventional moment diagrams. So typically a negative is a positive and vice versa. So in this case, well, you'll see that more again later, but I guess the easiest way to show that here is that instead of a concave up deflection here, or if you prefer a concave up deflection in RISA gives you a negative moment, whereas in our normal convention is a positive moment. All right, and you can also turn on the X, Y, and moment reactions, right? So you'll see that the external reactions show up here in green, and you see what they are. So here we have a 2.1 kip vertical reaction on the right and a 5.1 kip vertical reaction on the left. Right? So that's pretty much all the stuff that you would need to know about this frame, right? You need to know its shear, its moment, shear diagram, moment diagram, the reactions, the deflected shape. One other thing that you can do is there's this details button up here, and if you click on that, you get this different cursor, and then if you click on a member, you get a new window that pops up, and this is kind of a nice window. It gives you how long the member is, what the member number is, what joint is I and J, and then it gives you the charts that you might be interested in: axial force, shear, and moment, and then also the deflection, and it gives you numbers, right? So 5.069 kips, 3.379 kips of shear, and a maximum moment of 17.1 kip feet, right? It also gives you units here, and 4.4 inches of deflection, right? And the other cool thing is you can actually click on those diagrams, and it gives you a more detailed diagram, and there's a slider at the bottom, and you can move the slider across and it'll actually give you the values. So if you're looking for a value at a particular location, say the middle, it will give you that. Here you can see it's not actually 0, right? It's slightly different than 0. So that can be pretty powerful, particularly if, for example, you want to look at something like this, the beam, or member BC, and we have a moment diagram that is, in this case, it's parabolic, I guess. And so if you're after a particular value at a particular location, then you can kind of go and find that, right? So okay, so I think I've pretty much covered everything there. And then again, you can save this. One of the things that's interesting about this is that it saves it as an R2E file, which is different than RISA 2D or RISA 3D. So that is a little bit, which basically means that these two files are not compatible, right? You cannot take the simplified educational version and just drop the file into full version of R2D or R3D. So you will want to use this specifically for, this course and learning RISA, and then once you've got a pretty good handle on this, you can move on to the full version, which has a whole lot more buttons and a whole lot more capabilities. Okay, so that concludes my introduction to RISA.